I'll tell you what, on the deck,
when did you win? Okay, so like 6.5. I slept at 3.
I was probably
I slept at 3. I was going to wake up at 7.
I never seen stars.
I woke up at 7 because I slept. Yes, but remember, I took a longer journey.
I'm still in pain.
Okay, so you also stayed up until 7:30. Wait, so why did you say you got in time?
No.
You were late? Oh, so why did you start your alarm for 7? If you were only 5 to 10 minutes late, didn't you?
I thought that was for, I went for the other.
Oh.
I like,
So I think you're back in the opposite. I think you went for,
Yeah.
you opted for Russia.
I also got a question.
they don't know about that.
The question I asked was, so the guy said, like, what's the status of the portfolio? Like, we said status, what's the status of the yeah, it has to be because otherwise you can have different assets taking different states.
Yeah, so total state, right?
Yeah, it's like if you, it's like, well, it's, if you have number of states, I mean, not like number,
It's like M1 and the number of states of asset 1. And M1
exactly. I took max, right? Like max of F1, so N to the is the max number of states.
I think it's the M1 to M2.
Oh yeah.
Foundational papers have already very low. But then you end up getting like,
I thought that was fine. What do you think?
It was already like you have extra stuff on the work. So naturally, when they change the stuff, and then they'll use that.
Okay, but how, like, do you think taking natural object was it like,
I mean, you spend the natural life because I want to try
you could have guessed
even though the option is
oh, that's on Thursday.
I think we have this and the one
oh yeah.
I mean, you're
I'm going in February. Also, my doctor's, mainly because I have student science. Oh yeah.
I think I was talking to them.
Wait, actually, wait. This is just that'll come out really? So they have paintings like this in the
Yeah, I already like triple checked the keyboard, just like
these are like this the rest are not. Yeah, this is creased. When you ran last time, were you back?
Yeah.
You could I'm saying yeah, but do they have a spec? You might be rough.
mean, you know, the brand new thing
What?
was like,
The what? I'm gonna buy states.
Okay,
Maybe it's true.
so hello everyone. So I hope you're not in the wrong room. So this is ST418, the Advanced Time Series Analysis. And ST418, that's the course code. So if you're in the wrong room, so just like some previous students, so please be noted. Now, have a seat. So please, the first thing I want to introduce is the Moodle. So I've set up the Moodle page for this year, and so we'll have 2 seminars, if I remember correctly. So 2 seminar groups. So I suppose you can choose it on your LSC4U system. Okay. So which seminar group you prefer? So please do so, because our seminar is starting next week, and so one of the group I'll teach it myself here. The other group is taught by our GTA Kaizen Liu, so who is also my PhD student. So he's going to teach one of the seminar on Thursday. So it's Thursday and Friday. Okay. Okay. So I've written all the practicalities here. So it's about the homework. Okay. So we have from week 2 up to week 10, so we'll have homework. Okay, so you may argue that so there's already exercise 1 posted here, so it's just basically for you to get a little bit familiarize yourself with what is to come. Okay, so I introduced the R, because at least half of the exercises, and as well as the reading week exercise, which has a little bit of a case study. So you need to be familiar with R. So let me ask this. So are there any students who are not familiar with R? So I'll assume all of you are familiar somehow. Yeah? Because it's the homework, especially for the first half of the course. So I'll put our exercise there as well. So one important thing is that this course actually has a examination, which is 100% examination. So these coursework will not count towards the grade, but it's important for you to understand some of the practicalities in this time series analysis. Okay. So if you have any questions, please raise your hand and let me know. All right. Okay. And this exercise 1, so you can see that I've posted some of the links. Okay. I hope the mic is working better. So you can see that I post the links here with some of the data that we may look at in the course of the teachings in these 11 weeks. Okay, so and there's some very, very simple time series exercise. So I will not assume any basic time series knowledge, first of all. Okay, so I will go over quickly. Okay, I'll go over all the basics, maybe in the first 2 or at most 3 weeks, and then we'll go on to maybe a little bit deeper into some other topics. Okay, so the first 3 weeks, so we'll generally revisit some basic time series analysis. If you haven't done any time series, so that's good. So that will be your time to familiar with some basic stuffs. So let me go back to the Moodle first. So you can see that I have posted, where is it? The lecture notes. So the lecture notes is here on the Moodle page. So you can see lecture notes and handwritten notes. So these lecture notes, so everyone can download it. So if you are still not registered to the system, so please do let me know. So I think I still have one more student that I need to register as audit student, but if you can access this Moodle page somehow and download the lecture notes, so please let me know, okay? Send me an email. So this is the lecture note, so you can see that, so we have quite a number of topics. So the basic topics I've talked about is chapter 2. So I hope I can go over chapter 2 in a few weeks' time so that we can spend more time on the latter chapters in the learned, okay, which is more advanced topics. So this is the lecture note, and what are the handwritten notes? Handwritten notes are actually the notes I'm going to write on board through each lecture. So after writing, so I'll scan them and then upload it, okay? So during the lecture, so you can try to write what I'm writing down, but mainly try to listen to what I'm talking about in the lecture, because I'll scan everything I write and then upload onto Moodle, okay? So listening is the most important thing. And every lecture will have lecture recording, so it will be in this link. Exercise, I'll post it here, and for each exercise, you actually will have quite some time to finish. So I usually will post it on Tuesday. So for week 2 exercise onwards, so I'll post it on Tuesday, the coming Tuesday. And then you have Friday, until Friday next week, okay? Until Friday next week to finish, okay? So it's basically week 3 Friday, okay? For you to complete the week 2 homework, okay? So you have more than a week to finish the homework, and then upload it on the link provided. So I usually provide an upload link for the exercise, okay? So let's just say it's really important to finish this exercise, okay? So if anything, this exercise may not be enough, okay, for you to be completely familiar with the exams in the end. So you can see that this ST422 time series, this course ST418 is actually a evolution of ST422, which is now discontinued. But some of the topics overlap, so the basics especially overlapped. So you can see that I post all the examinations. So the course has run for 1 year, so we have last year as a fresh start. So later on, I'll post ST418 last year exams as well, okay? And so have a look at these exams somehow, maybe in the Easter, okay? But the exercise, most of the time, will involve topics that you need to know, okay? But to get more familiar with the certain type of questions, for instance, so maybe you should look at the exams as well, so these papers. So I have quite a number of years of exams for this course, all right? And the R code and data set. So this COVID-19 data set, so this will be involved in the future exercises, okay? So starting from next week, we have a series of exercises which involve this data set. And the London house price is an analysis in an example in the lecture notes. And the average house price in different regions of England. So this is a multivariate time series analysis. So this will be done in later chapters, as well as these 10 by 10 portfolios. Okay, so I've included all our scripts as well. So if you want to be a diligent student in advance, so you can look at all these out scripts and then try to run this data. So all the data are presented here. Okay. All right. So let's go back to what else? One important thing. So so for students who just come in, so if you're not familiar with R, so maybe you're shy, do not want to raise your hand, showing that you're not familiar. So if you're not familiar with R, so there's a pre-sessional course. So any student in LSC can take actually. So you just click in and then go through some very basic exercise. So how to read data, how to have simple analysis, so on and so forth. Okay, so this is important if you're not familiar with R. And the general discussion forum is for you to post questions, so it's anonymous. So if you have any questions about the course, so you can post it on here so that I can answer it. Or some other students, if they feel like it, so they can answer as well. And finally, so that's the new thing. So I think you have seen it multiple times already, maybe. So the use of generative AI. So generative AI policy. So because we don't have a project and the homework doesn't count towards the final grade, so this may be a less important point, but still, well, this course allows you to use the generative AI. So if you in homework, so you feel like it, so you can ask AI to try to do a part of it, as long as you state clearly. So this is done by AI. Okay, so writing some simple codes, I'm sure the AI can do that. So important thing is, from my experience, so if you let AI do the work, so it's most likely a zero-sum game. So AI do 50%, and you only learn 50%. So that's all I can say from my experience. Okay, so if you let AI do 90%, you're gonna learn 10%. So that's my experience. So I'll treat all of you as adults. So all of you are master students already, or some of you, I don't know, some of the students maybe PhD even. So try to measure your performance. Okay, try to measure how much you learn, and remember in the end, so there's a examination coming. So you will most likely, if nothing serious happens like in the COVID years, so we'll be having a sit-in exam still. So it's important you learn from the course the most. Okay. Anything else? Any questions? Okay. Good. So if you have any questions, let me know. All right. So let's get a quick start by looking at the topics first. So where's the... So these are the, let me make it larger. Okay, these are the topics, and so chapter 1 is just a brief introduction with some examples, so you can have a look. And if I have time, I'll have a look with you in the lectures. But mainly today, I'm going to dive into the basics in chapter 2. So this lecture and the next, and I think even the third lecture, I'm going to cover chapter 2. And I may not follow the order in chapter 3. So as long as I get some of the time series, basic time series explained, maybe I'll go to a part of chapter 3 to tell you, okay, how to do estimation and forecasting for those models, okay? So chapter 2 and chapter 3, so that's, the order is interchangeable. So as I see fit, okay? And the final topics in chapter 2 is the arch and gauge models. So they are financial time series. Okay, so I'll introduce some financial time series as well on top of these basic ARMA model. Okay, and then we'll go to, after all these topics, so how to forecast, how to estimate these models. So we'll go to multivariate time series. And this multivariate time series, so it will be on the latter half of the course, okay? So maybe starting from week 7, okay? So week 6 is a reading week, so I missed that. Week 6 is our reading week, okay? And so chapter 4 will be on multivariate time series. So this basically, most of the time is an extension for the basics from chapter 2, but there's some new concepts, of course, okay? So the gradual causality and also these sample cross correlation, so they perhaps are new concepts for you. And in chapter 5, definitely, so it will be new concepts, especially matrix time series factor model, okay? So we'll introduce factor model, and why do we need to do this for time series as well? So for the usual time series, which is multivariate time series, which is a factor of time series, and extend it to matrix time series. So what is matrix time series? So we'll give examples as well. So perhaps in this lecture actually, but in doing matrix time series analysis, so we'll do this in dimension reduction angle. Okay, so how do we, like factor model, how do we do dimension reduction in matrix time series? And how do we do dimension reduction in a way that will retain the structure of a matrix time series? Okay, so it's a matrix of data. So in the end, we want a matrix of data as forecasting or in estimation, all right? So how do we do that? So this final chapter of the course, all right? And so that's basically the very quick introduction. And so this is, in the first page, I talk about multivariate versus high dimensional time series. So that's the last page I'm going to do with you on screen, okay? So, and then I'll go to chapter 2, okay? So one concept about multivariate time series versus high dimensional time series is that multivariate time series usually involve analysis which assume that the number of time series you're looking at is fixed, okay? So for instance, if you have 1 year of financial data, so if we are talking about stock data, so 1 year is 250, okay, 252. So usually the number of trading days in 1 year. So your time points, sample size is 250, let's say. And so if you're looking at analyzing 1 time series or 2 time series with 250 sample size, okay, no problem. So let's do some time series modeling of these time series. Okay, so if number of time series you're looking at is 2, then it's a bivariate time series. Number of 3 or onwards, so people call it multivariate time series, right? But so it's still fixed. It's still a small number of time series you're looking at, okay? But instead, if you're looking at, let's say, 100 time series, for instance, if you're looking at, all the stocks in the FTSE 100, so there are 100 stocks, right? So you're looking at 100 time series of these returns, stock returns of FTSE 100 constituents. And you only have 1 year of trading data, so 250. So sample size 250, number of time series, so I usually denote by P in this course. So the dimension is 100. So 100 compared to 250, so that's significant, okay? So it's basically more like the sample size divided by 2, okay? So if we do any asymptotic analysis, which is usually the case in statistical analysis, so most of the more traditional analysis will, is asymptotic. So for instance, you do a lot of asymptotic analysis, assuming, let's say, your X bar is going to normal, right? Because the sample size is large, so the sample mean goes to a normal distribution, right? Something like that. So if you have the number of time series that is actually basically technically the order of the sample size. So here P is, in my set example, P is more like T over 2. So you really cannot say in my asymptotic analysis, so P is a fixed, right? Your asymptotic analysis is assuming the sample size is going to infinity. And now your P is actually T over 2. You cannot say P is fixed. So in this scenario, when your dimension is really high compared to the sample size, so you would say the dimension and the sample size diverge together, okay? They go to infinity together. And in this case, they go to infinity at the same order, okay? So P is the order of T, okay? So the constant is a half. So sometimes P is larger than T, okay? So if you want to analyze S&P 500, so 500 stocks, so if you only have 1 year of trading data, it's 250. So P is 2T, right? Rather than half a T. Okay. So, but it's still the same order as T, okay? So, but you're not assuming P is fixed in all these subsequent analysis, okay? That means what? That means the data we're looking at is not merely multivariate time series, which we assume P is fixed, but a high-dimensional time series. So high-dimensional time series, implicitly, we are saying that any asymptotic analysis results, we are assuming P and T diverge together. That's high-dimensional time series, okay? Okay, I'm not going to examine this with you, but this is important concept you need to know, okay? So what's the difference between multivariate and high-dimensional time series, okay? It's in terms of our asymptotic analysis. And practically, high-dimensional analysis, P is always assumed diverge with the sample size, all right? So that's the difference. And let me know if you have any questions, okay? So, but this is for your own good. So if you're going to pursue any further study, maybe PhD, I don't know, so it's good to know the difference between multivariate and high-dimensional time series. Now, let's go to, so all these details, please have a look, okay, if you're interested, okay? So the first thing we need, so first thing we want to go to is to introduce some basic notations, okay? So from now on, I'll use the .com. Can I paste this here as well? I don't know, there's only one screen. Okay. Anyway. Okay. So now this is the thing that I talk about in as handwritten note. Okay, so I'll go through things in this format, and then I'll upload what I've written down on Moodle. Okay. So important thing is to listen to me. Okay. So I'm going from chapter 2. So the basics. So let's introduce the notations we are going to use first. So the notations we're going to use is for univariate time series, so we use this xt as the notation, okay? And sometimes we'll imply that, so we have a set curly t for our time to denote a time series. So with time points t in this curly t, okay? So for multivariate or even high dimensional time series, so it's the same. So xt can be a higher order object or multivariate object. So xt itself can be higher order time series. So for instance, a matrix or even a higher order tensor. And in this course, we will look at T, which is countable. So if you do any stochastic analysis, stochastic calculus, or stochastic processor, so you study T, which is continuous, right? So diffusion process, etc. So we're not looking at that, okay? So we assume that we observe our time series at discrete times, okay? And practically even for diffusion process, so you assume a stop price is under diffusion process. So you also observe them only in discrete times, okay? So we have discrete time points. But the random variable themselves can take a continuous value, of course. So the random variable xt, so each random variable, so I denote by rv. So rv from here on denote random variable. So each random variable xt itself can take continuous values. Right. So the first thing is to differentiate between just xt and a bracket xt. Bracket xt is a sequence, basically, a series. Xt is any random variable inside this sequence or series, okay? And, okay, so how do we do any how do we extract any insight from this xt? Okay, so in this course, so we'll place certain assumption on this time series. Okay. So for instance, if you're looking at some summary statistic, and most summary statistics, the most useful one usually are the moments, okay? So first order, second order moments, so which we'll talk about later on, what these means. And if you want to extract these summary statistics, so you need to assume a certain conditions so that the observed data can actually be summarized into these summary statistics, okay? For instance, if you have a time series actually is increasing exponentially, then it's really not making any sense to talk about is there a mean of this time series, right? So it's increasing exponentially over time. So there's really not a stable average then for this time series, okay? So whenever we talk about this stable first order or second order moments, we assume certain kind of stationarity for time series, okay? And to introduce stationarity, so let's look at a concept called strong stationarity first. Or some people call it strict stationarity. So this strong or strict stationarity has a very rigorous definition. So you're given a time series xt. Now you can see that I don't have any set under writing as a subscript here. So I assume that the set is basically all integers, including -1, okay? So t, maybe the time series starts from -infinity, okay, to positive infinity. And given xt and given any integer, t1, t2, up to tm, let's say, and a constant h. So you have m different time points, t1, t2, up to tm, and a constant h. The definition involves this probability statement. So if xt1 is less than or equal to a1, xt2 less than or equal to a2 up to xt m is less than or equal to am, then this will equal to the probability of xt1 plus h less than or equal to a1 all the way up to xtm plus h less than or equal to am. But what are the a's? So for any given constants, so they are also constant, but they are arbitrary constants, a1 up to am. So if this is the case, then we say xt is strongly stationary, okay? So what do I mean by strong stationarity then? If you look at the probability statement in this definition, so this is actually multivariate cumulative distribution function, okay? So we are basically looking at multivariate CDF, okay? So I write down all the full forms in the first time, and then I'll write abbreviations from here on. So we are looking at multivariate CDF. And the left-hand side is a multivariate CDF for this xt1, xt2 up to xtm factor, okay? What is the right-hand side? Well, the right-hand side is another factor, but all the time points are shifted by a time lag h, okay? And we are saying that the both multivariate CDF are actually the same, okay? So this statement is basically stating that multivariate CDF is the same. Under a constant time shift. Or later on we'll use lag. So under a constant time lag, h. And the factor we are looking at is xt1 up to xtm shifted by h to xt1 plus h up to xtm plus h, okay? So both factor will have the same multivariate CDF. But they are actually arbitrary from the time series xt itself, right? We pick m different time points, pick the corresponding random variables to form a factor, and all of them as a factor will have the same multivariate CDF under any constant time shift h. That's what it means by strong stationarity, okay? And this is quite strong actually, so the distribution is the same. That means what? That means all the moments are the same. You have first order moments, so that's the mean of all the random variables. You have second order moments. Second order moments involve the cross multiplication of all these xti's. Third order moment and so on, okay? They are all the same for these two vectors, okay? That's what it means by distribution, basically the same, okay? So it means all the moments from first order to infinity order, as long as they are finite, they are the same, okay? So this is really strong. And let's look at some simple implication in a little bit more detail. So let's say if we look at m equals to 1. So you have m-dimensional factor on the left-hand side and m-dimensional factor on the right-hand side. But if we are looking at m equals to 1, then we are just looking at univariate factor, right? Basically just univariate time series. Then the definition boils down to xt1 less than a1 equals to probability of xt1 plus h is less than or equal to a1. And that means what? That means what? That means if the first order moment, so first order moment exists. So if first order moment exists under this assumption, then expectation of xt1 is going to be the same as expectation of xt1 plus h, right? They have the same CDF after all. They have the same distribution. So of course their mean is the same, if the mean exists. And let's say this is a constant mu, which is time independent. So no matter what time point you're looking at, whatever time shift h you're looking at, so they have the same mean. So it's time independent. That's the first implication. So if we look at m equals to 2, then the statement becomes xt1 less than a1 and xt2 less than a2 equals to xt1 plus h less than a1 and xt2 plus h is less than a2. So what is the implication of that? If second order moment exists, second order just means, well, first of all, the square term or the cross products, okay? So as long as they multiply to second order degree, as in the definition in a polynomial, second order degree polynomial, then it's second order moment. So as this cross order moments, xt1, xt2, And it's going to be equal to, under this assumption, xt1 plus h times xt2 plus h, right? So at the same time, the expectation of xt I squared also equals to expectation of xt I plus h squared for both time points I equals 1 and 2, right? That's all the second order moments. Okay? So you can imagine as you go to third or even fourth order moments, that's going to be more complicated, more restrictions. Okay? So strong stationarity is really a strong assumption actually. But in this course, we're usually looking at the second order moments up to, which usually contain the most information about the time series. So if these two are valid, then it implies that the covariance between xt1 and xt2, remember covariance formula, so a covariance of xt1 and xt2 is what? Is the expectation of xt1 times xt2 minus the expectation of xt1 and xt2, okay? So this is going to be equal to covariance between xt1 plus h and xt2 plus h, okay? And therefore the covariance is just a, let me make it in the middle. So covariance is just a function. So function is abbreviated at FCN here. So it's just a function of the distance between your time points. Okay? As long as the distance between the time point here, the distance is what? The absolute value of t1 minus t2. That's the distance. Here the distance, h is cancelled out, so it's still absolute value of t1 minus t2. So it's a function of the distance between the time points that you're looking at for the time series. So covariance is just a function of t1 minus t2. Not the time points themselves, but the distance between the time points you're looking at. So what does this imply? So it implies that we can place a little more definition on the moments, the first two order moments of xt. So if xt is strongly stationary, then we can define a sequence as h which is the covariance between xt and xt plus h. So h is called a time lag here, okay? So it's just a function of time lag h. And we call sh the autocovariance sequence. So in the duration of the course, so you'll see a lot of this term ACVS, okay? So autocovariance sequence is a concept derived from stationarity, okay? So here is strong stationarity. Later on, we'll assume a much weaker condition for stationarity, which is called weak stationarity later on. But they both direct you towards the definition of autocovariant sequence for your time series. Okay? So this autocovariant sequence is the covariance between xt and xt plus h, whatever t is, because of stationarity. Okay? So it just depends on the time lag h, or the time shift. H is the distance between t and t plus h. All right? And all these inspire us to use estimators like X bar, because first order moment is time independent, and as soon as it's finite, then we can estimate it from our data. So this X bar makes sense because the population mean is time independent, okay? Under the stationarity assumption. As well as the second order moments. So X bar. And this SH hat, so T minus absolute value of H. Is xt minus x bar times xt plus h minus x bar. Whatever lag h you're looking at, it can be negative, it can be positive. Okay, so therefore we put absolute value here. Okay, so if you have done any fundamental statistics, it's basically just the taking covariance between xt and xt plus h, okay? Xt plus absolute value of h, okay? For estimating mu and sh, sh is the covariance between xt and xt plus h, right? So practically, that's how we estimate it, okay? And your data here, of course, is just x1, x2, up to x capital T, okay? So in this course, we usually use capital T to denote our sample size, all right? These x1 up to xt are value that we observe, okay? So these are basically random variables we assume that we can observe, okay? So these X bar and SH hat, they are estimators for the mean mu and SH respectively, okay? So it inspires stationarity, inspires all these concepts and the corresponding estimators if we have the data to estimate them, okay? Any questions so far? These are basic concepts, okay? These are basic concepts. So if you have any questions, let me know, okay? Or post in the discussion forum, it's anonymous, or just drop me an email, okay? I will reply to you, okay? And let's continue with a little bit more before I give you, say, a 10-minute break, okay? So I'll give you a break. Okay. So far, so good. So we have introduced a concept of strong stationarity and the implication on the first two order of moments, if they exist, okay? And how do we estimate them if we have data? But this strong stationarity, as I said, is really a strong assumption. In particular, if you're looking at higher order moments, then those higher order moments have also to be time independent. Okay? So you can easily use the method I have used previously for m equals 1, m equals 2 to derive this understanding that higher order moments are also time independent. Okay. So this is too strong. Okay. In particular, in most of the statistical analysis, we usually only extract information from the first two order of moments. For instance, the mean and also the second order moments. Okay, that's usually the case. So assuming further moments are also time independent is a very, very strong assumption that we do not want to make. And that's why we want to introduce something called weak stationarity, as opposed to strong stationarity, stationarity. So weak stationarity, we want to introduce this because strong stationarity I would say in most applications, not all, is too strong. Most applications only require us to extract up to second order information for any analysis. Okay, so for XT, you're given a time series. So what is weak stationarity? If we have, first of all, you need to have the expectation of xt equals to a constant mean mu, which is finite. Less than infinity means finite, okay? So that is time independent as well. Time independent and finite. The second point is the covariance between xt and xt plus h equals to a certain value which is dependent on h only, not time itself, but just the time lag between the time points of the random variables we are considering. And they have to be finite as well. So that is so a function of time lag. And finite. So with these two, then we say xt is weakly stationary. Okay. Okay, I think it's a good time to give you a break. Okay, so this is almost 2. I'll give you 7 minutes, so please come back at 2:05. Okay. Okay. So let's continue. Now, before I go into some examples, so let's look at some of the examples in the lecture note. Okay, so this is chapter 1, page 6. Okay, so this is global temperature deviations data. I take this as example because you can replicate it in R. Okay, so I think I have also shown you what's the data set in R. So all of these data sets in the package ASTSA. Okay, so if you look at the library ASTSA, what? So if you load up this library, so let's say you want to look at the global temperature data, so you can actually plot it. Okay. Is it in the mass library then? Maybe it's not in the new. Maybe it's not in the new version of our studio. So it used to be there. But if I find out which data set is now in, I will let you know. Okay. But my main point is, so you can plot this data. So this is the global temperature data, okay? So this is a very simple time series, a simple univariate time series. And you can see this is certainly not, over time is not really stationary, first of all. So there's a increasing trend for the global temperature, okay? From 1880 up to early 2000, okay? So this is the data set. So if you look at this range, then certainly it's not stationary. If there's a larger range, is it going to be non-stationary still? So then we don't know, okay? So perhaps this is just one small artifact of later on you'll learn what autoregressive model is. Perhaps this is just a certain seasonality, okay? So we don't know. If we look at a larger time scale, is it going to be stationary? Well, we don't know. Okay, so we can only say that so within this range. Okay, this certainly does not look stationary, but in a larger time scale, perhaps it's still non-stationary. Perhaps it's actually stationary. So we don't know. Okay, so that's the first thing I want you to know. So all this stationarity, practically, we need to look at the data range. Okay. And if you look at the, let's skip this. So if you look at this earthquake data, so this is also supposedly in the Mars library, but I don't know if it's here or not now. Perhaps not. So this earthquake data, you can see this is basically a seismic reading of earthquake and also an explosion. Okay. So supposedly an explosion is nearby the measuring device for the seismic reading. Okay, so let's look at the earthquake data first. So from 0 to 1,000, I think this is just millisecond, okay? Or even, it should be millisecond, I think. So it's before the earthquake, and then right after 1,000, so the earthquake started, and you can clearly see that even with your naked eye, that the time series behave differently. Okay, so perhaps the mean may stay the same, but well, its variance certainly is not. At the same time, the variation frequency is different also. You can see that. So before t equals to 1,000. It fluctuates more rapidly, okay? But after time 1,000, after the earthquake started, so it fluctuates with a rhythm, okay, and with a magnitude as well, okay. So it's basically like most earthquake, okay. So the magnitude of vibration on the Earth crust, of course, is very violent. So the magnitude increase as well as it has a rhythm, okay. And it's because this rhythm is slower than the usual rhythm of the Earth, which is basically a lot of random noise added together. So it has a liquid sand effect that will sink any buildings, right? So this is the reason why the building or bridges sink, right? Because the vibration rhythm make the ground appears like the ocean, okay? So appears like a liquid. So people say it's liquefied, okay? So liquefied sand or liquefied ground after an earthquake, okay? So this is consistent with what we observed. So more rhythmic and more violent vibration of the Earth. And the same as explosion. Explosion is a little bit different. So you can see that before, again, time 1000 is before the explosion. So right after the explosion, the seismic reading increased, okay? But different from an earthquake, so its rhythm is similar actually. So I mean the frequency of vibration, you can see that is similar, but the magnitude is way larger than the usual, right? Of course, so after explosion, so the magnitude of vibration of course increased, but it doesn't vibrate like an earthquake. It doesn't have a rhythm, okay? So an explosion doesn't create a liquefied effect of the ground, right? Okay, so my point is, so these two time series still don't look stationary. Now before time 1000, so maybe look stationary, so certain amplitude with certain mean, but not seeing it as a whole, okay? So for the earthquake data after 1000, so it may be still stationary, so with a larger amplitude, larger frequency of vibration, a smaller frequency of vibration. But looking at the whole time series, of course, anyone can see that is not going to be stationary. Okay, so stationarity can be, usually we look at in the first and second order moments. At the same time, practically stationarity needs to have a time range, okay? So if you look at localized data, if you look at time period from 1500 to 2000 here, well, it looks stationary, okay? So it's a time range that matters, okay? It's basically the same as what I've said for the global temperature data. So if we look at a longer time range for global temperature, which perhaps we should be, then perhaps we maybe cannot conclude that the temperature is really varying out of control, okay? It's all about time scale, okay? All right. So I hope all these are still here. Yeah, I don't know if EQ5 is still here. Let's have a look. Okay, the earthquake data is here. Okay. So I'll play around. You can plot this. Okay. Yeah. So it's basically the same plot as your It's basically the same plot as your lecture notes. Right, so let's go back to the concepts that we were looking at. So we were looking at weak stationarity. So here, the data certainly does not look like weakly stationary, but before time 1000, perhaps it is. And after 1000, it is also, but not when we look at them together, okay? So what are the examples? So I will give you some the most simple examples of weak stationarity of time series. So let's go back to .com here. just let's look at this example. So the first one, so we can consider XT for an IID. So that's the notation I'm going to use, IID normal mu sigma square. That means all the XTs are independent and identically distributed as normal distribution with mean mu and variance sigma square. Then of course XT is strongly stationary. No matter what factors you compose drawing random variables from this time series, well, they are IID normal mean mu with variance sigma square, okay? And the covariance, they're all zero, okay? So they're all finite, and covariance, well, basically all zero, except when time lag equals zero. When time lag equals zero, we're looking at variance, which is also finite and time independent, equals to sigma square, okay? So it is indeed strongly stationary and weakly stationary as well. So another example, which is related to your exercise 2, so I will post it on Tuesday. Okay, so if I give you this time series, so when t is even, they follow IID random standard normal. And when t is odd, well, distribution change. They are still IID, but they are uniform. So uniform distribution from minus A to A. So I pose you a question, so can you find A? So that XT is weakly stationary. So not all A will make it weakly stationary, but some A will. So can you find an A so that this time series is weakly stationary? So what does it entail? Well, if you remember the definition, so the mean has to be the same for all t, and they're finite. Okay, so the mean for when t is even is 0. So when t is odd, what is the mean? The mean is 0 still. So the mean is okay, but how about covariance? Well, covariance doesn't matter. They're all IID. As long as the time point is not the same, the covariance is 0. So time independent and finite. But how about variances? Well, variance of xt when t is even is 1. How about variance of xt when t is odd? Well, that depends on A, right? So we need to make it 1 in order that the whole time series xt can be considered as weakly stationary, right? Okay, so I'll let you figure it out. So this is just in-class exercise. So it should be a very simple exercise, okay? So let me continue. To give another definition, so the autocorrelation function, so we call it ACF, okay? ACF. Is rho h equals to the ACVS SH divided by S0. Remember SH has the definition of covariance between xt and xt plus h. So S0 is what? Variance of xt. So, is it correspond to correlation between two random variables? Well, you bet it is. Your row H is actually covariance between xt and xt plus h. Of course, we are assuming weak stationarity here, at least. So divided by the variance of xt times the variance of xt plus h. The numerator here is, by definition, our sh, the ACVS at leg h. How about the denominator? So that's the square root of variance of xt is S0. Variance of xt plus h is S0, okay? They are time independent, right? So that equals to sh divided by S0, okay? So that indeed is just the correlation between xt and xt plus h, and we called it the autocorrelation function. Function in the sense that it's a function of the time lag h, okay? So people will usually look at the ACF for a time series and determine some characteristic of it, okay? But before we go to these more simple time series, starting from white noise and then autoregressive models. So perhaps some of you may have learned that already. Well, before that, so I introduce another concept. Your master students, okay? So therefore, I will need to do this. So here is the concept of what we call positive semi-definiteness of the autocovariance sequence, the CVS. So let me give you a definition. So for a sequence, so I abbreviated as SEQ, okay, for a sequence, SH. It's just a sequence, okay, so it may not be a CVS of anything, okay. It's just a sequence. I named it as SH. So if we have so it's a double sum here, let's say. So it's AI times AJ times S of HI minus HJ. So it's larger than 0, respectively larger than or equal to 0 for any constants A1 up to AM. And we also involve constant H1 up to HM. These are all time lags in this sequence, okay? Then we say the sequence SH is positive definite. PD. So respectively, if it's larger than 0, it's called positive definite, abbreviated as PD. If it's larger than or equal to 0, so it's called positive semi-definite. Abbreviated as PSD. Okay? So why do I suddenly introduce a little bit weird concept here? Well, it's actually connected with what we have talked about. So let me give you the simplest example I can think of. So let's consider the sequence, which is a finite sequence. Let's just say it's 0.4, 1, and then 0.4, okay? And this sequence is, in fact, positive definite, okay? So you can find any HIHJ is just basically 1 and 0, okay? So it's just 0 and 1, HI and HJ. So there are only 3 numbers here, okay? And it's symmetric around the middle one, okay? So you can number H is from -1, 0 to 1, okay? You can also number it as 1, 2, 3, no problem. The result will be the same, okay? If we number it as -1, 0, and 1, okay? And then you substitute these numbers in for any AI and AJ, so it all will be larger than 0. And this is one way to look at it. So how do we know that this is indeed larger than 0? So we define xt equals to x1, x2. So it's just a finite time series with 2 random variables, okay? And the variance of all xt equals to 1. And the covariance between x1 and x2 is 0.4. So this is valid, okay? So any covariance can take between x1 and x2. And SH is actually the ACVS of xt, right? So for the ACVS, for finite time series, so it's basically a symmetric one, okay? So symmetric on minus and plus h, okay? And it certainly has an odd number of entries in this SH, okay? If it's not infinite, okay? So if it's finite, so it starts from minus h. So here, there are 2 random variables only, so lag is only 1. The maximum number of lags is only 1, okay, so x1 and x2. So we start with -1, and then 0, and then 1. So that's the lags, okay? And this sequence here is exactly the ACVS of this very short time series xt. And actually there's a theorem. So you just need to know this, okay? So SH is actually PSD or PD, if and only if. So IFF is if and only if, okay? If and only if. This sequence SH is the ACVS of some weekly stationary time series. So this star here is something you need to know, okay? So this sequence is positive semi-definite if and only if the sequence itself is the ACVS of some weekly stationary time series. So if you can show that it's ACVS of some weekly stationary time series, then this sequence is certainly at least positive semi-definite, or it could be positive definite. In this case, in this particular example, it's actually positive definite, okay? So you don't need to know how to prove that, but you need to know the connection. So I suppose most of you will know positive semi-definite or positive definiteness through matrix, right? positive definiteness of a matrix is a more familiar concept to you. So how is it connect to positive definiteness of a matrix? Let's say in this example, if we let xt in fact, if we let x equals to the whole time series extracted, which is just two random variables, it's a bivariate time series x1, x2, then what's the variance of x? Variance of x is the variance covariance matrix, right? Okay. So if I go through these and you find some concepts very unfamiliar, so that means there's a gap, okay? So if there's a gap, so you need to let me know, and you need to catch up, okay? So this, we are talking about bivariate time series here. What is the or multivariate time series here? What is the variance of a factor of time series? So this is a variance covariance matrix. With all the variance on the diagonal, variance of x is 1, okay? So that's 1, and the covariance is 0.4, okay? This corresponds to covariance of x1 and x2. This corresponds to covariance of x2 and x1, which of course is equals to covariance of x1 and x2. It's symmetric. So the variance covariance matrix will be a symmetric matrix. And this matrix is what? Is in fact positive definite. This is in matrix sense, okay? The matrix here, the variance of x is positive definite. So if we are given any constants a1 and a2, let's say this vector a equals to the column vector a1, a2, so the transpose here, I denote T by the transpose. And A transpose times the variance of x times A is what? Is actually just the variance of A transpose x. Right? Variance of any matrix multiplied with a factor is the matrix times the variance times the matrix transpose. Okay? So here the formula I'm using is the variance of any matrix B multiplied with a factor y is the constant matrix times the variance of y times B transpose, right? So if anyone finds that this is totally unfamiliar, so you need to catch up with a little bit of this basics multivariate statistics, okay? This is just statistics, not time series, okay? And after this example, I'll go to the supplementary material, okay? I'll introduce a little bit. Okay, so listen to me first. So this A transpose X is the variance of A1 x1 plus A2 x2, right? And any variance of any random variable, of course, is larger than or equal to 0. And using this formula, this equals to A transpose times variance x times A. So this equals to A1, A2, the row factor times this matrix times this column factor, right? So what's my point? My point is this is exactly the sum that are used in the definition of positive semi-definiteness for a sequence. So this is Si minus j. So any A1, A2, so try to multiply it out and see. And see this is correct. So this is your job. Okay, so positive definiteness of a sequence through looking in the angle of the variance of a variance of a factor of time series, they are basically the same, correspond to each other. Okay, so positive definiteness or positive definiteness of a sequence correspond to positive definiteness of a certain matrix, the variance covariance matrix of the time series involved. Okay, so they correspond to each other. So that's why this definition of sequence is still also called positive semi-definiteness, same as the matrix sense of positive semi-definiteness, because they correspond to each other. Okay, it's just that we have this concept because of a stationary time series, and it corresponds to the PD concept of in a matrix sense. Okay. Okay, good. So if you find the things I'm talking about starting to be unfamiliar, so I was looking at the supplementary material, which is at the bottom of the Moodle. So if you open it, so this will be the file. So the supplementary material for ST418. So I introduced a little bit of matrix algebra. So what is eigenvalue, eigenvector? Okay, and so I hope you all have these concepts. If you don't, have a look, and better consult some very basic linear algebra textbook. At the same time, so I introduced the concept of diagonalizability. Okay, so because it's a statistics course, so usually the matrix we're looking at is symmetric, or most likely symmetric, positive, definite, right? We're looking at variance, covariance matrix of a factor of random variables. So they're usually symmetric, positive, definite. And these matrices have the property that, so it can be diagonalizable, and usually can be diagonalizable in such a way that Q inverse will be Q transpose, okay? So they're diagonalizable and also with real eigenvalues, okay? So real eigenvalues come with real symmetric matrix, all right? And some of these concepts will come in handy. So positive definiteness, so I connect this to why a quadratic form like this will be larger than or equal to 0, okay? So positive definiteness in the matrix sense will be any quadratic form for the matrix will be positive or non-negative at least, okay? Quadratic form means I have a vector, I take a transpose, multiply with the matrix times the vector itself. That's a quadratic form in A, okay? Any quadratic form involving a positive semi-definite matrix A will be non-negative, okay? That's the origin of the name positive definiteness or positive semi-definiteness, okay? So all these are basics, okay? So if you don't have these concepts, so have a look at this material and better consult some linear algebra textbook. It doesn't need to go deep, so at least eigenvalues, eigenvectors, for symmetric real matrix, what is the implication of these, okay? And this one I'm going to talk about later. So I linked this to this positive semi-definiteness of sequence as well, okay? So have a look, all right? In this example 3 and example 4 as well, okay? So later on, so there are other concepts, okay? So I'll only talk about that when we are in there, all right? So the message is, so if you have any questions, so if you find any gap in knowledge, so let me know, and see if I can give you any advice of what textbook to look at, and if you think the questions, if you can post the question on the discussion forum, even better, so some other students can share. Most likely, we'll share the same problem as you, so that we can contribute to the knowledge of others as well, as I answer them. All right? Or if you like, just drop me an email, okay? All right. So let's continue. Okay, good. ST410, so the next concept, we'll talk about the Gaussian process. I'll give a definition. Later on, we'll come back when we talk about financial time series. Okay, so this is later. This concept will come back. So Gaussian process. So what is a Gaussian process? So if xt is such that, again, we pick out, say, m different time points, belongs to a certain set I, and x equals to a vector formed by picking out all the corresponding random variables corresponding those time points. Then this has a Gaussian distribution. So Gaussian distribution, so it's normal distribution. Well, it's a factor here, so when I say normal distribution, it means what? It means multivariate normal distribution, okay? And xt is a Gaussian process. All right. Well, this is another concept, okay? So don't mix it up with stationarity. So here, xt does not need to be stationary. So I never talk about time independent and stuff. So as long as I pick random variables from this time series and form a random vector, it follows a multivariate normal distribution, then it's a Gaussian process. This multivariate normal distribution can have highly time-dependent mean and covariance. I don't care. So as long as it's multivariate normal, it's a Gaussian process, okay? So it doesn't need to be stationary. For this Gaussian process definition per se. So example, the simplest example, so IID normal, let's say with mean mu t, variance sigma square. So the mean is time dependent, variance is not, covariance is 0, so it's still time dependent. So first order moment time dependent, second order moment is not. Well, still, xt is Gaussian. So we say it's Gaussian, that means it's a Gaussian process, okay? So you pick any times random variables from this time series, form a random vector, so well, the multivariate mean is complicated mu t, okay? So mu t1, mu t2 up to mu tm, okay? So it's time dependent, but it's a multivariate normal nevertheless, because they are IID normal random variable put together in a vector, they are jointly normal. So this is a very special property of multivariate normal, okay? So this is not necessarily true when you talk about other distributions, okay? Other multivariate distributions. So even IID, some other type of distributions put together, is it jointly that kind of distribution? Well, it may not. But normal distribution has this property, okay? ID normal random variables put together as a vector is jointly normal. Okay. Jointly normal means the random vector has a multivariate normal distribution. Yeah, I shouldn't write this. Let me give a condition first. So if your xt is weakly stationary, and Gaussian, then what do you have? Then xt is strongly stationary. So that's the link to the concepts we've introduced. So we've introduced the stationarity, and this Gaussian process doesn't even need to be stationary. But if we have a process which is Gaussian and also weakly stationary, so what does it mean? It means it's strongly stationary as well. So I can even give a quick proof of that. So the proof is very simple. So let a vector y equals to xt1, xt2 up to xtm. And this is drawn from with the xti's drawn from a normal distribution. Right? They're Gaussian, so all the xti's are normal. So it's normal because it's Gaussian, so the random vector has to be multivariate normal by definition of Gaussian process. But normal with mean what? With mean equals to, because it's weakly stationary as well, so the mean has to be, let's say, equals to mu. Now mu is just a scalar, so there are m of them, xt1 up to xtm. So it's mu times a factor of 1s. So it's a factor of 1. And there are m of them. So a vector of 1s of length m. That is definition of 1m here. So mu times this, so it's a factor of mu, the m of them, okay? Because the expectation of a random vector is just the random factor of the expectation of each random variable, which they are all mean mu, okay? Because it's weakly stationary. So it's time independent. And let's say the covariance matrix is sigma. So what is sigma here? Sigma is, first of all, an m by m matrix, and equals to, what's the ij entry? The ij entry is the covariance between xti and xtj, right? So that's sigma here. So sigma is just denotes the second order moments, the variance covariance matrix of this factor xt1 up to xtn. Okay. So this is just the variance of y. So we have this normal distribution for this particular random factor y, that we basically arbitrarily construct from picking m random time points. Now what? Well, we want to prove is strongly stationary, so let's consider another vector. Let's say YH. So this time it's all shifted. Remember, strong stationarity needs multivariate CDF to be equal for the time shifted random vector as well, right? So first of all, this is also Gaussian. So Gaussianity of xt implies that YH is also Gaussian. In distribution. And what's the mean of this YH? Expectation of YH is, well, it's weakly stationary time series by the assumption, so it's still mu times 1m. And this is from weak stationarity. And what's the variance? Well, variance of YH is, variance of YH is, individual definition is for the ij entry, xti plus h, taking covariance of xtj plus h, right? But the distance between them, well, is xti minus tj. By weak stationarity, it's just the same as covariance of xti and xtj, right? This is by weak stationarity. Weak stationarity. And what is this matrix? This is just sigma. And therefore, YH also follows a multivariate normal with mean equals to mu 1m and variance covariance matrix sigma, which has the same distribution as Y. Well, that's proof complete, right? That's exactly what we want. Strong stationarity means these two vectors have the same distribution. And that's exactly what we proved here, okay? Therefore, this statement holds. So, this statement. So if xt is weakly stationary and Gaussian, it is also strongly stationary, okay? And so you may ask me, okay, what's the usage of this? Well, the usage of this is in research purpose, if you are assuming weak stationarity for very relaxed assumption, but if somehow you need to assume any Gaussian distribution in your time series, then you're basically doing a very strong assumption. You're basically doing strong stationarity. Okay, so it's basically a warning that you thought your assumption is weak, but actually combined, it implies a very strong assumption. Okay. So that's basically more for research purpose usually. So we cannot, if we really want a relaxed assumption in your analysis from the get-go, usually you cannot assume is Gaussian. That's basically the message, okay? Yeah. All right. Let me see how much time. I don't have enough time to add another topic, so I think that's it for today. Tuesday, so I'll post a new exercise, okay, related to these concepts, all right? So I'll see you guys next week. Seminars start next week, okay? So if you haven't chosen a seminar slot, please choose it on the LC4U system, all right?
Wait, this is a tripping video.
Number like 2 months to reach this.
Wait, I'll open for this one to stop. So I think if you think about it, open it, he responded for it, like on the same day for you. But like, quite nice. But you might want to talk about it.
Hi.
Thank you so much for the project. Something because I have I would actually really like to. Oh yeah, it's true. But I believe there was like my intention to take this. Can I still do it?
I don't know. Are you allowed to do that on the system?
Yes. So we can still do the changes.
Yeah, I think so, right? It's still week 1. So, yeah.
So if I submit it on
Yeah, I'll check it tonight, okay? I'll check the request tonight and then I'll okay?
Great. Thank you so
Yeah,
much.
okay.
I'll be really grateful.
Yep. Yep.
Thanks so much.
No problem.
Thank you.
Thank you very much.
Thank you.
Actually, now it makes me think that my whole data science project assumes some stationarity of stuff, which is the whole.